Hi, in this video we're going to be looking at the uncertainty principle. We have a particle that it's in a state described by this wave function. We have the domain where the particle exists. We know that B is a constant. And we want to make sure that by calculating certain parameters, we can make a comment about the uncertainty principle that relates the position with the momentum of this specific particle. So how do we do that? Remember that the statement of the uncertainty principle that it's applicable in this case is the uncertainty in the distance times the position times the uncertainty in the momentum along the same direction should be larger or equal to a constant, in this case h bar over 2. So that means we have to recall what are the definitions for those uncertainties for both the position, it's given here, and the momentum. And remember, this is basically the definition of standard deviation, where we have to calculate the expectation values of two different entities. The first one is, for example, in case of the momentum square, or the square of the expectation of the momentum. In the case of the position, the expectation value of the position square and the expectation value square of the position. So in this case, in order to make those predictions according to these calculations, these definitions, we first have to calculate all the following expectation values, the ones that are included in these two formulas. Then once we have each one of those expectation values, we can combine them and substitute them in each of the expressions to evaluate the corresponding uncertainties. And finally, depending on the product between those two uncertainties, we can make a comment regarding the agreement or disagreement between our result and the uncertainty principle. So let's get into it. Since we have to calculate expectation values of observables, our observables being both the position and the momentum, just recall the general expression for the expectation value of an observable. Remember that the expectation value of that observable means that I'm going to insert these operator corresponding to that particular observable in the expression of the probability density. And it's acting on the function that is directly to its right. Now, this particular operator is going to change depending on the kind of observable that we're calculating. Let's do the first one, that is calculating the square of the expectation value of the position. So expectation value times expectation value. So that means that we only have to calculate the expectation value of the position once, and then we multiply the value that we get by itself in order to get the square of that. Now, make sure to look at this expression. The analogy that we have now is my observable is the position, my operator is going to be the position operator. And in that particular case, remember that we have the explicit form of my wave functions. I'm substituting in each of the sides wave function star, the complex conjugate of that, times the wave function. And the position operator is just multiplication by the position, in this case by x. Another thing that you have to make sure that you remember, this is the most general expression, the complex conjugate of my function, but in this particular case, you can see that the function is a real valued function. So the complex conjugate in this case, it's going to be equal to the wave function itself. And also another thing that you want to remember is that since we have exponentials here, the multiplication of two exponentials, the exponents just get added together. So we perform all the multiplications that we can. What we end up having is the product of two functions, the position, x, times my original wave function square. Remember that once we have set up this problem, we can start thinking about the math, and we can actually use Mathematica to do that. This is the definition. We're looking at the expectation value of my position. We are defining the wave function just exactly as the one that was given here. So that's the one that we're defining here. The very first thing that I'm going to ask you is always make sure that the function is normalized. In this case, you have a constant in front of this exponential. So it may be tempting to say that it is normalized. That should be the normalization constant, but it's not necessarily the case. It could be just a constant. So in this case, we're going to be assuming that this constant value is a positive real number. So that's the condition that I'm assigning here when I'm solving in Mathematica. And then remember that the expression is just going to be the complex conjugate of my function times the wave function to calculate the probability density. And then I have to integrate over all space in order to get the normalization constant. That's a normalization condition. And overall space in this case for my problem is from minus infinity to infinity. So that's all space in this particular case. So I set up the equations, and yes, I got that the integral is equal to 1. So that means that this particular function is normalized. So now I can move on to do any other calculations. Now, what we have in this particular case is x times my wave function square, the probability density. And what I want to do before even checking what the value of the corresponding integral is, I just want to check one of those suggestions that I've been making over and over again, which is just get a feeling for the characteristics of your problem. And with that, basically what you can do is let's plot the integrand, the function of the integrand, to see how that behaves. And I'm just going to be plotting in a particular range, and I'm just giving a series of numbers to beta to be, because it's a constant value, I'm just giving a series of values of beta, so it actually, Mathematica can plot it. If I don't give values to beta, Mathematica doesn't know what to do with this one, it will not plot anything. So I really need to give specific constant values to that parameter. And look what I have. This is the function of my integrand. Now, by changing the parameter beta, what you can see is just that the function becomes more narrow or gets wider. And then you can immediately see also with here, this button, just what the values, particular values of beta you're applying. Anyway, but the important part here is the shape of the integrand, because what we're going to be doing is integrating all the way from minus infinity to infinity. And what you can see is that given this is an odd function, the integral should be equal to 0. So we're going to plot it. We're going to be doing it now in Mathematica to make sure that that is actually the case. But if by having this idea of how the function looks like, we immediately know that the integral must be 0. So now that's what we're going to be doing here. We're going to check that the expression that we have integrated from minus infinity to infinity should give me 0. There you go. That is the result that we were expecting, because again, the integrand. So I'm urging you to always plot to have a good feeling for the physics of your problem. What your wave function is representing. Now with that, we come back to our problem, and then since we know that this integral is equal to 0, 0 times a constant is 0, and then the expectation value for your particle is 0. And now if the expectation value of the position is 0, 0 times 0 is also 0. So this particular expectation value, or the square of the expectation value, should be equal to 0. Now, what that is telling you in terms of the expectation value is that if you were to do a series of measurements, random measurements, over a large sampling of experimental measurements, the average value, the expectation value for the position will be exactly 0. And again, that from the form of the function that we're integrating, the position times the probability density values are going to be averaged to that center point. Okay, so we have the first. Let's go to the second one. Now we want to calculate the expectation value of the position square. It is not the same. Now, if you look at my operator, the operator is going to be x squared, which is equal to apply the position operator twice. Now, with that, since the position operator is just multiplication by x, then the second time is multiplication by x again. So I end up having that this operator is just multiplication by x squared. So the setup of the problem is similar to what we had before. I substitute the values of my wave functions. Don't forget to have the complex conjugate. But again, in this case, the function is real value, so complex conjugate is equal to the wave function. But I don't want you to forget that in case your function is a complex function, if you write it always like this, you will not miss the fact that you have to complex conjugate your function. So even though this is real, that's why I'm still including this value just for other cases where you have that. Don't forget to complex conjugate your function. Anyway, we can factor out some terms. We can take out this particular constant, and then this is the function that we have to integrate now. It's x squared times this one square. That gives me 2 times beta x squared. Let's do the same idea as before. Now we are trying to calculate the expectation value of the position square, where my operator is position operator square. We're defining the wave function the same way as we did before. So let's input that. Same idea. Let's see how this behaves. Let's see how the integrand behaves. And this is what we find. Now, this is an even function. And as you can see, if we are integrating from minus infinity to infinity, there's no, this is, again, an even function. It's not going to cancel out, like in the case of the odd functions where we have a negative and a positive part. In this case, we have 2 positive parts. It's going to add up to a constant value. So in this case, we know that it's not going to be 0. So let's see what the value is. And another thing that I wanted to remind you, I've been posting these in the answer keys or answer guides for some of the problems, that in cases where your function is even, and if I'm integrating from minus infinity to infinity, is the same as integrating twice from 0 to infinity. And the reason for that is, again, because if you integrate on one side, it's exactly the same integral in value that if you integrate from the middle to the right. So in total, you can say, I'm going to integrate only this part and multiply it twice to get the total integral. And if you were to use tables, the integral that you most likely will see is of this form, from 0 to infinity instead of minus infinity to infinity. So that's something to have in mind. And what I'm doing here in Mathematica is just confirming that those two will have to give me exactly the same result. And yes, sure enough, I get exactly the same thing when I'm integrating from minus infinity to infinity or twice from 0 to infinity. So this is the value of the integral that I wanted to get. And just to be consistent, according to the calculation that I set up here, what I have is x squared times this function. And that's exactly what I wanted to calculate here with Mathematica. This one already includes the constant in my definition of psi. But again, just to be consistent with what I had, I need to calculate this particular integral. So this is the one that I have here, and when I calculate that, it gives me this value. So this is the one that I'm going to use just to continue the solution of this problem, and that's exactly what I got here as my result. And now here I can just simplify, and finally I end up having 1 over 4 times beta, which again is the same value that I got when I included the normalization constant in the definition of psi. Good. So that is the value of the expectation of the position square. And remember that I need these two to define the standard deviation in the position. Now let's do similar calculations, but for the momentum, where I have to calculate the expectation value for the momentum, and I square that, and then I calculate the expectation value of the momentum square. Let's do with the easier one first. Remember the same idea. If this is square, it's the same as applying the momentum operator once, and then I can square the value that I get. So my definition, according to the general equation for the expectation value of my observable, I can substitute now. If I want to know the expectation value of the momentum, I substitute or insert that momentum operator in my probability density. And by definition, we know that in quantum mechanics, this momentum operator is equal to minus I h bar and times the differential with respect to x of my function. This is what the operator acting on my function is. So let's do the proper substitutions. I end up now that I'm going to take the derivative of this function, and then that is going to be multiplied by the complex conjugate of my function, and then I can integrate it. So let's see. Let's get rid of some of the constants first, and then we can take the derivative of the exponential here. And since it's just the first derivative with respect to x, we end up having minus 2 times beta x times the original function, or times the original exponential in this case. Then we can take out all the constants together, and then we end up cleaning up a little bit my integral, and this is what I have to solve. Now, again, you can look it up on a table, or you can use Mathematica for that. So same idea. We're now trying to get the expectation value for the momentum. We define our wave function. We can calculate the momentum operator, or the result of applying the momentum operator into my wave function by the same way that we define it here. This will be just to kind of check our work that we did manually. Let's check it out in Mathematica. And this is the same result that we had. Plus some constants that, remember that the way that I'm doing it here, I'm cleaning up the constants before going into that. In Mathematica, I already included the constant in my function. But if you look at that, those are equivalent. Well, let's check the form of the integral, of the integrand. And this is what we get. The integrand being the complex conjugate of my function times what I got from applying the momentum operator to that function. All of those are constant, or constants values. This function x times this function. This is the integrand that I'm plotting here. The same idea as before. Beta is just changing our distribution, but it's still an odd function. Then we will be expecting that the integral is equal to 0. So let's just make sure that that is the case. Yes, it is 0. Same as what we had for the position operator. It's the same form. So let's go back to our problem, and this integral is going to be equal to 0. And then with that, we know that the expectation value of the momentum, 0, then the square of that is still equal to 0. So we have the first element in here. Now let's go to calculate the most complicated part of this problem, which is calculating the expectation value of the momentum square. Now, the expectation value of the momentum square is applying the momentum twice. So the first time we do what we already had, and then we apply the momentum again. And also in class, we discussed that this momentum operator square is equal to minus h bar squared times the second derivative of the function that we have in front of us, or that you have in front of the operator. So that is in total. Let's do the proper substitutions. Keep track of where the constants are going. And then here we have my complex conjugate function times the second derivative of this exponential function. So now this one, when we take the second derivative, we ended up with this value, where we have now a sum of 2 functions. This first term times this function minus the second term times the exponential function. So we can expand that, and then we can say that by factoring out 2 beta here, just to kind of try to clean up my equation as much as possible, then we end up with a bunch of constants, and then we have 2 integrals that we can solve separately. So let's see what we can say about that particular function. So let's calculate now the expectation value of the momentum square. So let's define our wave function first. Let's just check that what we had as our second derivative of our wave function is correct. So this is to double check our work. And then, yeah, sure enough, what we have here, just after some cleanup, is exactly what we end up having in this particular case. Now, I'm just assigning the momentum square operator times my acting on my wave function as this variable phi, just to simplify the work that we have in here. So let's do this, and that is going to give me now this particular value. So it's also a non-zero value. But since I am writing here the solution partially by hand, then just to be consistent, let's actually make sure that whatever I am writing in here is actually the results are correct. So in this case, we'll be taking the second derivative of this function, and that's what I'm going to test with this expression. I'm going to calculate the second derivative with respect to x of my function, which is e to the minus beta x squared. And yes, that's exactly what I got in here. So check mark for me. And then again, just to be consistent, the integrals that I am actually ended up having to solve is this integral, the integral from minus infinity to infinity of x squared times e to the minus 2 beta x squared, which is the product of these two multiplied together. And on the other hand, I'm going to have the integral from minus infinity to infinity of these two multiplied together, which gives me this. So those are the integrals that I have to solve in this case, just to be consistent with the way that I'm writing my answer here. And with that, those are the values that I got. And I am substituting those values in here for each of them. And then I just have to simplify the equation, just do my algebra to get the result of h bar squared times beta, which again is the same as what I got before. I'm just doing here to show you how to set up the problem, since I was working out this partially by hand. You do some of these cleanup of the calculations by hand and then insert those into Mathematica. And the reason for that is I think it's a good exercise for you to kind of keep track of what you're doing to make sense of the calculations that you're putting onto the computer. And that way, the more you understand what you're doing, the easier the problems are going to become. You have to be very well aware of what you are putting into the software. Remember that. The computer is just going to give you whatever you ask it to do. Okay, so this is the expectation value of the momentum square, non-zero. So in summary, what we had is two expectation values that were zero, both of them related to the expectation value of both the position and the momentum. Both of them are zero. When we square them are going to be zero. And then two non-zero terms, which are these expectation values of the operator square. We bring up the values, so I end up with this quantity for the uncertainty in the position. I'm going to do similar to the momentum, where this one was zero, this one was h bar squared times beta, so I end up with this value. When we put them together, multiplying one times the other, what we end up having is uncertainty in the position times uncertainty in the momentum is equal to h bar over 2. So that is consistent what we have in terms of the expectation for the uncertainty principle. And we just notice in particular that this result is exactly the smallest possible uncertainty that we can have. Because remember that the uncertainties between two are bound by this equal value. They can always be larger, but never lower. The lower bound is always when this relationship equals h bar over 2, and this is exactly what we have in this particular case. In summary, what we did is, given a wave function that describes the state of a particle, we calculated different expectation values for the momentum and the position, and we put them together in order to calculate now the standard deviations of those observables, position and momentum. And then by multiplying those uncertainties, standard deviations, together, then I get the expression that corresponds to the uncertainty principle for this particular system. And I noticed that it's exactly at the lowest bound for the statement regarding this general statement of the uncertainty principle. Okay, so this is how you do this type of calculations. I hope this is helpful. With that, I'm signing off.